Okay, so we're going to look at hydraulics. And hydraulics is basically a force multiplier or a distance multiplier because that's the relationship, right? Of pressure is force divided by area. So that's a relationship of the two. So the cool thing is, as you saw from the hydraulics video, is that you can move something a short distance and it comes out as a multiplier on the other end. So you can move a great force. So Pascal's principle really is talking about the fact that the pressure in a contained fluid is the same everywhere in the fluid. So if I push down on here, let's say I push down and I ended up with 40 pascals of pressure, everywhere in here is also experiencing 40 pascals of pressure, including up on this piston. It's kind of like when you inflate a balloon. You're exerting 40, and if it was, let's say, 4 pascals of pressure, but those 4 pascals of pressure are being pressed out everywhere equally on the balloon. So if you're in a confined area, the pressure is the same everywhere within that area. Now, since the balloon expands, we know obviously it's an unbalanced force. But if I push down with 40 pascals, I put down, let's say, pressure, creating 40 pascals of pressure, then 40 pascals of pressure would push up on this side. Now, if I change the diameter of this piston, either larger or smaller, I can actually change the distance or the force that it can lift. So, same size piston is just force transfer. Same either way. What I push down is what I can lift up on the other side. But if I go from a really small opening piston on one side to a larger opening here, I'll have to push the small side down farther. But since this side is so much larger, I can lift a much larger force. It just won't lift as high. So if I push this down 10 centimeters, this might only lift 1 centimeter depending on the relationship of the pressure within the system. So small to big is a force multiplier. Same size is just transfer of force. So there's one more, big to small. If I push down on a large size, I don't move it very far, but it can shoot the other side out without any effort at all. And it'll be hard for me to push that large one down, but it will have very little resistance on the other side. And that is a distance multiplier. In other words, I push down here, shoots the other side out. Kind of like if you have someone, I just want to make sure this is on mute because we don't need the sound, but this is kind of the cool way to look at this. And you say, okay, so she's pressing down with a force on one side, and that is multiplying because the higher up they go, the farther they have to fall, creating higher and higher force, which exerts the pressure on the other side. In other words, they're transferring their momentum too, is another way to look at it. So this is actually looking at how force can make somebody else's distance change. Now, right now, it's pretty much even up. They're going you'll notice pretty much the same on both sides. Now, to stop this, it's interesting how they stop. They actually have to change their distance from the center to create less and less force so that they can actually stop without having to fall completely to the ground. And you see she's moving in. And as she moves in, she can stop that transfer. This is one that I'm actually going to say go ahead and watch if you wish. And remember, this stuff is also in the notes in the folder that says notes reference only. You can always go back and look at any of this again.
Hydraulics might sound complicated, but all they are is another force multiplier. They utilize the fact that liquids are virtually incompressible, which means when you compress them, the pressure you apply to one point of the liquid is transmitted equally in all directions.
So this is in the set of notes, but the other place you're going to watch it is right after this. I'm going to actually have this as an Edpuzzle so that you can watch the whole thing. We get into copyright issues if I play the whole thing through, but it is in the notes too, so if you ever need to go back and look at it, it's there. So let's do some math. Let's apply that stuff you've learned where you know that force divided by area, and we'll use small a for area because big A is acceleration, and in this case we're going to call pascals for pressure, okay, is force divided by area. So in this case, just pretend all of these are the right units and squared. okay. It's just, we're going to go with that. We're not going to do any transitions and tweaking. I should, but we don't have time to do that right now. So I want to find out what the pressure in this fluid is. I can go either way. In this case, my force is 10 newtons divided by my area, 2 square centimeters, which means my pressure is 5 pascals. And that would be the answer. So that means everywhere in this fluid, I'm exerting 5 pascals of pressure there, and there, and there, and there, and there, and that means up on this one. And if this is going down, then this pressure is 5 pascals going up. And interestingly enough, if we take this backwards, 5 pascals times my area gives me the force out. So 5 times 10 means that by putting in, on the smaller side, 10 newtons of force, I can lift 50 newtons. I'm going to have to press this down a really long way. This won't rise as far, but I can lift something 5 times heavier just because I've changed those distances. All right, so if I wanted to go through, I could do the same thing here, but this is going, if I'm going down here, I have a larger area on this side. I'm not going to lift as far, but I will be able to lift a heavier object. So let's look at number 2. We're going to actually do this math. And first of all, we need to see what we're looking for. And that is, what will the force upward on the larger piston be? That means we have to do 2 different things. First of all, we have to determine what is the pressure inside here before we can calculate the force up. So in this case, pressure is going to be 20 newtons divided by 5, well, it's meters squared, but we're just going to pretend that it's the right unit. And that would end up being 4 pascals. Okay? Now, if this is 4 PA everywhere in this fluid, then up would be 4 pascals times the 10 meters squared. So that means I'm lifting 40 newtons of force. So by putting in 10, I can lift 40. Number 3, what is the pressure in this hydraulic system? Well, again, that's 20 force divided by area. 20 divided by 5 is 4 pascals. Should have probably put that one first, but it all works. So if I went and looked at number 4, do the same thing here without going through that. Do you notice that if this is 4 times 10 is 40, it's a difference of a factor. It's lifting twice the amount. I could go down here and figure out that 100 divided by that is a difference of 100-fold. 15 divided by 3 is a difference of 5. And in this case, going the other way, 50 divided by 2 would be 25. And that's just the ratio. What is the ratio? What's the force multiplier in this? How much more can I lift? Here I'm lifting 100 times more. Here I'm only lifting 5 times more. But here I'm lifting 25 times more. So again, if this was drawn to scale, we'd have obviously much larger surface area here and small, tiny compared to that, but we just put numbers in for you to look at that. This is really doing that second attempt at practical application math. This is in that folder. You can go and practice this if you want. It's not required, but you certainly can. So again, if we took and we actually measured this distance across and figured out what the surface area is, we could in fact figure out what that relationship is just by doing a little measurement. And how do you find the area of a circle? So you need a formula. If you need assistance or have questions on this set of notes, as always, ask.